let's finish this example problem up, shall we? So again, what are we trying to do? Well, we've got this piping system, perfectly normal looking piping system, copper tubing, which probably wouldn't see that today in a house, but that's okay. Let's say we've got copper tubing coming in, say 10-foot link coming in, 10-foot going up, 10-foot link going through the crawl space in between the first and second floor, 10 more feet up, and then 20 feet over through a globe valve into a faucet that's going to fill us up a bathtub. Right? So we have an elevation increase of 20 feet from the inlet to the outlet. We've already accommodated that. It's a smaller diameter at the outlet, so there's a kinetic energy change. Part A we've already done. Neglect all losses. Part B, neglect the minor losses. That's what we just finished up with. And then Part C says with no losses. So that's going to include the minor losses now. So again, Part A, to overcome the increase in elevation, we needed about 14.44 psi. That's in an ideal flow situation. This is not ideal flow. We've got about 60 feet of pipe. That's going to increase the pressure loss by an additional 27 psi. So to overcome the major loss in the Bernoulli expectation, we're going to need about 41.5 psi additional to get there. Now, Part C says neglect. So for Part C, neglect no losses. That means include minor losses. So what that means is that the energy loss, which is still going to include this FL over D V squared over 2, which we've already done this, but now I've also got sum KL, the summation of all the minor loss coefficients times the average kinetic energy flowing through all of those connections. Now again, we've already quantified this. That's up here. Right? Now I need to quantify this quantity. Well, to do that, I need to know what do these fittings look like. Well, they told us in the initial problem statement. I've got threaded 90-degree elbows. There's 4 of them. 1, 2, 3, 4. I've got a fully open globe valve. And then I've got a faucet that they were nice enough in the problem statement to give me a minor loss coefficient of 2. So I need to look up the minor loss coefficients for these guys. The globe valve. What I would suggest is build you a little table here of what you have. A lot of times I call it the fitting or a description, something like that. Quantity, how many of them do you have? Minor loss, each. And the total KL for that particular fitting. So I've got 90-degree threaded. I've got 4 of those. I've got 1 globe valve open, and then I've got, and the reason this is going to be overkill on something this simple because I've just got a few entries. But if I've got a really complex system with lots of unions, lots of elbows, lots of valves, you probably want to build a table to do this. And I've got this faucet. I've got 1 of each of these. We know the faucet has a minor loss for each faucet of 2, so there's only 2 of those. I'm sorry, there's only 1 of those, so that's a total minor loss of 2 on that. The others we need to look up. Okay? And that's marked page in my text here. I'm in the 3rd edition of Chengel and Symbala, where they tell us that, I don't know if you guys can see that there. Let me see if I can. Yeah, perfect. So I'm just going to assume these are smooth bends, threaded, right? So I'm going to assume that this is a correct approximate value for it, and they're saying if it's threaded, the minor loss is 0.9. Okay? And then down here it's got some different valves. It's saying that if I've got a globe valve fully open, I've got a minor loss of 10. So I'm going to write those down. So 0.9 for the fitting for the elbows, and 10 for the fully open globe valve. So, there's my cat. I don't know if you guys can hear her. She's going to say hello to us. 90-degree threaded elbows are 0.9. So 4 times 0.9, I'm getting, that looks a lot like 3.6 to me. I don't know about you guys. One fully open globe valve, the text said that a 10 is a good approximation. These are just approximations. We would measure these in an ideal condition and try to report an average value. And that's what that text value is giving us, is just kind of an average value. Somebody did a lot of research, measured a bunch of these, and kind of figured out, okay, well, the average 90-degree threaded would give about a 0.9 minor loss for any kinetic energy. Right? So what we have to do then is I need a total minor loss coefficient, total of all these. I've got 3.6, I've got 10, and I've got 2. So that is, looks an awful lot like 15.6 to me. Right? And what the heck do we do with that? Well, again, we want to try to find the energy loss. We've already found this quantity. Now I need to find this quantity. So the energy loss, the minor portion of the energy loss. This is the major portion. We're now looking at the minor portion. That is sum KL V squared over 2. Well, let's assume that it's V1 flowing through all of these. Now, we could get into an argument about, well, this 2 in the faucet, should this be V2 or V1? And truth is, it's an approximation either way. I'm going to keep this simple. Let's say it's V1 because it's V1 coming into it. So let's just assume that V1 is a sufficient average for that one as well. And so this then just simply becomes that sum KL, which is 15.6, times V1. Again, we're going to approximate V1 as a good average velocity or average speed moving through this stuff. It's 14.52 is what I have written here. Feet per second. That's going to get squared, divided by 2. So the minor loss, the minor energy loss. Let's see, I've got this in feet squared per second squared. I've got 1645.5, we'll say. Feet squared per second squared. So that's what I have if you run these numbers here. Maybe that's wrong. Demonstrated in a few videos that I can be wrong, so double check this on your calculator as you're going. Trying to go slow enough you can kind of keep up writing and triple checking your numbers in the calculator so you don't fall asleep on me. Can't imagine these videos would be really boring if you're just watching me and not actually writing this down or taking notes and running your calculator. It's good practice. So the minor pressure loss, as we've already established, which is going to be rho E loss, okay, so that's 62.41 pound mass per cubic foot. That's the density, times this 1645.5 feet squared per second squared. And then we're going to go ahead and do the conversion factors we've been doing all along. All right. If you're just joining us, go back and watch the other videos so this part makes sense. There's 1 pound force second squared for every 32.2 pound mass feet. That's going to leave me with pound force feet, pound force per foot squared. Let's get rid of the feet squared. So for every square foot, there's 144 square inches. That'll leave us with PSI, which is what we want. So the minor loss is going to be 22. I've got here on my spreadsheet 22.15. That's pound force per inch squared, or PSI. So, the inlet gauge pressure required, all the way back here, the initial problem statement, we said the initial gauge pressure required is going to be rho times this quantity plus this quantity plus the energy loss. Okay, well, this, of course, has major and minor losses, and we found all of those now, right? So this is going to be this rho V2 squared minus V1 squared over 2 plus GZ2 plus times E loss major plus rho times E loss minor. Right? I'm a little repetitive here, and that's okay. I'm getting about, let's say, 14.44 psi G for this one, plus we said about 27.03 psi for the major loss, and then I've just found about 22.15 psi for the minor loss. Very close to the major loss. So the gauge pressure required to maintain this, again, the whole goal is to try to get 20 gallons per minute into this bathtub, get in the piping system. To do that, I need to add all these pressures up. I need to maintain an inlet pressure of, my spreadsheet's telling me here, about 63.6 psi G. That's gauge pressure. So if I put a pressure gauge at the main entrance coming into this piping system, or probably coming into the house, if I put a pressure gauge in there, I need at least this pressure to try to force 20 gallons per minute into this faucet coming out. If I have less pressure than that coming in from a source, maybe I need to hook up a pump. Maybe I need to call the city and complain. I don't know. There are other vehicles, and that's for later courses that we can get into to get to that. But that's a nice example. Get us going on this particular set of lectures. That is a major and minor loss component example. We'll pick up there next time. Good luck, guys. Stay healthy out there. Loud pop.